Hello everybody. Thanks to the organizing committee for providing this platform to speak in this event on the domain of biohydrogen production. My presentation will briefly highlight on fermentative hydrogen production process development by using aquatic macrophyte, algae and other woody biomass as the non-food competitive next generation feed. As we all know that the global energy demand is increasing concomitantly, and with rising population, this energy demand has been expected to increase by 40% in coming 2 decades. India is the third largest consumer of crude oil in the world, and the major share of this oil demand, energy demand, is being fulfilled by the crude oil import. In order to meet the rising energy demand, of course, it is very much essential to explore for the alternative energy production processes that do not depend on the conventional fossil fuel-based resources. Among various alternate energy forms, hydrogen has been gained global attention as the significant energy form that has a potential for a low carbon economy. It has a high energy content which is around 2.75 times higher than the hydrocarbon fuels. It is carbon dioxide neutral, and as a feedstock, this energy form has a great potential to penetrate in power sectors for electricity generation, in transport sector, and has a key role in decarbonization. Hydrogen market has a total estimated value of $115 billion and that has been projected to rise significantly to around $155 billion by 2022. Hence, it is very much essential to explore for the alternate hydrogen production technologies from the non-fossil based resources. Currently, around 70 million tons of hydrogen is being produced globally per annum. As you can see that major fraction of this hydrogen is being generated from the conventional fossil-based resources. That is more than 70% from the natural gas, around 16 to 18% from the coal, and only a small fraction, that is 7 to 9% of hydrogen is being generated through the electrolysis process by water splitting. Global hydrogen demand has been projected to rise around 530 million tons per annum by 2050. So major concern of these processes is that the current hydrogen production processes are they are associated with the release of carbon dioxide because mostly they are produced from the fossil-based resources. And currently hydrogen is being used mostly by the two industries like fertilizer industries for the ammonia production and for the hydrotreatment, hydrocratic process by the refinery. As this slide shows, current hydrogen production technologies or processes are highly energy intensive, and the major concern is the release of greenhouse gas during production of hydrogen from these fossil-based resources. Compared with the biological process for hydrogen production, they are more environmental friendly and less energy intensive, as these biological processes can be operated at ambient temperature and pressure, and they are not associated with the release of hazardous greenhouse gas and can be generated from the non-fossil resources. Hence, they are sustainable. Based on the type of pathways involved for the hydrogen production by select microbes, these biological processes are categorized into 4 different processes like dark fermentation process. As the name indicates, some microbes, they encompass the pathway to produce hydrogen in absence of light. That means they do not require light as a source of energy, and these microbes could feed on the sugary substrate to produce hydrogen through the anaerobic process. The significant aspect of this process is that the rate of hydrogen evolution is high, and these microbes could feed on the organic waste to produce hydrogen, and the input sugary substrate, they are not converted into the complete, they are not completely assimilated during this pathway, and this pathway leads to the production of the intermediate metabolites, mostly the organic acids. The hydrogen yield efficiency thus is little less compared to the other processes. In case of photofermentation process, few of the microbes like purple non-sulfur bacteria, these microbes, they encompass the pathway to produce hydrogen in presence of light through fermentation pathway in anaerobic process, and these microbes could feed on the short chain organic acids to produce hydrogen, and the hydrogen yield efficiency is comparatively higher through this process. However, the rate of the reaction is comparatively slower when we compare to the dark fermentation process. In case of photosynthetic process, few of the select algae and cyanobacteria like spirulina and chlamydomonas, they have been reported to produce hydrogen through the photosynthetic process, and water is the feed, that is the significant aspect of this process. However, the rate of the reaction is low when we compare with the dark fermentation process, and this process also requires light as this photofermentation process as a source of energy. The another constraint of this process is the release of oxygen during this photosynthetic process, because oxygen inhibits the catalytic reaction of the hydrogenase enzyme that catalyzes for the production of hydrogen during this photosynthetic process. And the fourth process is the integration of dark fermentation process with the photofermentation process. As I have mentioned, during this dark fermentation process, these microbes, they generate intermediate metabolites like organic acids, and these organic acids can be utilized by these photofermentative bacteria to produce hydrogen. Hence, this process can be integrated with this dark fermentation process that can lead to the production of hydrogen with high yield efficiency close to the theoretical yield limit and with a high titer. As the input sugar, the common input sugar can be used as a feed for production of hydrogen through both these processes that can completely utilize this sugar into CO2 and S2. Considering the significant aspects of this dark fermentation process, that is the high rate of hydrogen evolution and use of the waste organic material as a feed for hydrogen production, globally this process has been extensively explored by the scientists to produce hydrogen from an array of substrates. And like I mentioned, only few microbes, they encompass this pathway, that is the Clostridium, Enterobacter, Citrobacter and Bacillus. Through this pathway, maximum 4 mole of hydrogen can be generated from 1 mole of glucose in case the acetic acid is the intermediate metabolite. This hydrogen yield efficiency goes low when the intermediate metabolite is the butyric acid. In view of this, we have started our research explorations or production of hydrogen from next generation non-food competitive feed, the woody biomass and aquatic plant and algae a decade back. This is the approach that we have followed. We have isolated the samples across the nation from the eastern, western, northern and southern region of the country, with a goal to enrich the microbes to selectively isolate the hydrogen producing microbes with high yield efficiency and high titer. We have, like I mentioned, we have enriched all these samples in anaerobic growth mode using different nutrient media as reported in the literature, and those microbial consortia were selected based on the hydrogen production performance and the consortium that could produce high hydrogen yield or titer with high yield efficiency we have selected for purification of the microbe, hydrogen producing microbe. After purifying the select microbes, we have optimized the parameters, that is both environmental as well as nutritional parameters, to enhance the catalytic efficiency of the hydrogenase enzyme with a goal to enhance the yield efficiency from different substrates. Eventually, these microbes were used for scale up of this hydrogen production process under standardized condition to monitor the reproducibility of hydrogen yield efficiency and the titer of these microbes from different substrates. As I mentioned, our major goal was to look for the avenues for using lignocellulose biomass as feed for the hydrogen production. As we can see, globally around 220 billion tons of biomass are being generated. If we can tap the energy that is entrapped in this biomass in the form of carbohydrate, we can generate energy that is equivalent to 60 to 80 billion tons of crude oil. However, it is essential to convert this biomass or the complex carbohydrates from this biomass to the simple forms, because this biomass contains mostly three different fractions, that is the lignin, cellulose and hemicellulose. The challenge lies in the fractionation of these components and this conversion of these complex carbohydrates to the simple. Once these carbohydrates are converted to the simple monomers, then it can be used as a potential feed for hydrogen. Apart from using the woody biomass, we have also explored to use this aquatic plant like water hyacinth, azolla and also microalgae as a next generation feed, the non-food competitive feed for production of hydrogen. As you can see here, water hyacinth is a very aquatic invasive species that multiplies very fast in the wetlands, and it has been estimated that more than 450 tons of water hyacinth biomass is being generated per hectare per year in India. Water hyacinth biomass, and it is very much essential to remove this biomass, this water hyacinth from the aquatic bodies in order to protect the flora and fauna underlying in the water bodies. This biomass, they contain more than 50% fraction of this biomass is the carbohydrate, and this carbohydrate can be used as a very good feed for production of hydrogen. And the pre-treatment of this aquatic plant is comparatively easier because this lignin fraction is comparatively less, which is around less than 10% of this biomass. Azolla is another aquatic plant. In fact, this is an aquatic fern that grows faster. It has a gestation time, growth time of around 5 to 6 days. This fern can grow in contaminated water, whether it is domestic grey water, and it has a high biomass productivity. Around 12 tons of this biomass can be generated per hectare per year. Again, the lignin fraction of this biomass is very less than 5%. Hence, it is relatively easy for pre-treatment of this biomass. Apart from that, if we see the microalgae, these are also very good biomass that has a great potential to use as a feed, because the microalgae has a faster growth rate, and these forms, they do not compete with the agricultural land. And of course, microalgae cultivation got the wide attention because of their CO2 sequestration potential. And the microalgae biomass, they contain around 18 to 20%, or some forms are reported to produce higher, to generate higher fraction of lipids, that is more than 20%. So after extraction of lipid, this biomass, which contains around 20 to 25% of carbohydrate, can be used again as a feed for production of biofuel, that is hydrogen. So algae biomass also offers as a platform biomass to produce different biofuels in a biorefinery approach. As I mentioned that the major challenge lies for this woody biomass is the pre-treatment, that is separation of the lignin and then eventually saccharification of this complex carbohydrates, that is cellulose and hemicellulose, into the monomers of pentose and hexose. So almost all the microbes are reported to feed on the hexose sugar. However, only few microbes are reported which can feed on the pentose sugar to produce hydrogen. Hence, we have selectively enriched the microbes, like I have mentioned in my previous slides, to enrich for the microbe that could utilize both pentose and hexose. Only then it is feasible to extract all the energy forms which are present in this woody or lignocellulose biomass in the form of cellulose and hemicellulose to convert to the biofuel forms. So we were successful in isolating a microbe that is Enterobacter glauci. The strain is TT1, and this strain could utilize both pentose and hexose sugars to produce hydrogen. And as you can see here, this microbe could produce 2.6 moles of hydrogen per mole of pentose sugar out of maximum 3.3 mole of hydrogen per mole of xylose, which is the maximum theoretical yield efficiency. That means this has a more than 80% hydrogen yield efficiency from the pentose sugar, and further this microbe could also utilize glucose, this hexose, to produce hydrogen. And we have also screened this microbe to produce hydrogen from a broad spectrum biomass sugars like wheat straw, rice straw, sugarcane bagasse, sorghum stubble, and aquatic plant biomass. And eventually we have scaled this process for hydrogen production by using this microbe as a host in 30-liter bioreactor under standardized condition, and the results were reproducible. We have the qualitative assessment we have done by gas chromatographic analysis, and for the quantitative hydrogen production was monitored by the water displacement method. Like I mentioned, we have also monitored the hydrogen production performance of the select microbe from sorghum stubble, rice straw, sugarcane bagasse, azolla biomass, water hyacinth, wheat straw, and the results were quite promising. So this microbe could utilize all these biomass sugars to produce hydrogen with more than 70% yield efficiency as compared to the theoretical efficiency of this microbe. We have published work, and eventually we have also scaled up this hydrogen production process by using this Enterobacter as a cell factory to produce hydrogen from all these different type of biomass, that is the sugarcane bagasse, wheat straw, and rice straw. Initially, these biomass samples were pre-treated through the acid hydrolysis process, and the acid hydrolysis process released the pentose-rich hydrolysate. Those hydrolysate samples also we have used as a feed for production of hydrogen, and eventually the residual biomass after acid treatment we have hydrolyzed with different enzymes to convert to the monomers, and those samples were further used for the scale-up of hydrogen production as this slide shows. Eventually we have scaled up this process in 30-liter bioreactor, and then 200-liter bioreactor, and the qualitative assessment of this biogas production was done by gas chromatographic analysis. The biogas was mainly composed of hydrogen and CO2. The proportion of hydrogen in the biogas was around 50 to 55%, and the CO2 proportion was around 35 to 40%. Somewhere it is 45%. No other gas production was observed during this process, and because these processes are anaerobic, we have carried out all these scale-up processes under anaerobic condition by purging with nitrogen that was generated from the in-house nitrogen gas reactor generator. The generated nitrogen with 99.999% purity, as we can see here, and we have successfully scaled up this process in 200-liter scale, and this process has further potential to scale up in the larger and pre-demonstration scale, so that that can eventually pave the way for commercialization of the process in the larger scale. And to make this process sustainable, it is also very much essential to use the spent effluent after this biogas production, which is rich in short chain organic acids, that is acetic acid and butyric acid, for production of further hydrogen either through the photofermentation process or for production of the methane by integrating with the biogas production in the second stage. Eventually, we have developed the process for treatment of these aquatic plants, that is the water hyacinth, for conversion into the simple sugars. We have developed a acid treatment process for conversion of water hyacinth into the monomers, first with the acid treatment, and the residual biomass was further hydrolyzed with the enzyme to convert the cellulose and hemicellulose fractions again to the monomer. And we have also developed a process, like I mentioned, for large-scale cultivation of azolla by using the domestic grey water, and then the azolla which is generated is again being subjected for the pre-treatment for conversion into the simple sugars. This water hyacinth biomass was composed of around 40 to 50% of carbohydrates. Major fraction of the carbohydrate was hemicellulose. In case of azolla, the carbohydrate fraction was around 55%. So accordingly, we have scaled this pre-treatment and enzyme hydrolysis process for conversion of this biomass into the simple sugar. And thus, after conversion of this biomass to the simple sugars, those biomass sugars we have used as a feed to produce hydrogen, and then that process was eventually upscaled. This slide shows this scale up of this process for hydrogen production from this water hyacinth biomass and the azolla biomass. This is the 30-liter bioreactor, and the working volume was 20 liter. And we have also scaled up in 100-liter scale, and are currently scaling up this process further in the 1000-liter scale is in progress. Currently, the process has been developed in a pilot scale, but the current challenge is the cost economy of the process. In order to make this process cost economically viable, it is very much essential to integrate this biofuel production process with production of other biocommodities, valuated biocommodities that has a application potential in downstream industries. So in that case, the spent effluent, as I have mentioned earlier also, the spent effluent, which is mainly rich in the acetic acid and butyric acid, either those acids can be extracted, which are the high value organic acids. Those acids are produced at a rate of 0.35 to 4% in the broth. Otherwise, those acids can also be channelized to produce the fuel or other commodity chemicals eventually by integrating with other biological processes. So this process not only leads to the cleaning of the water bodies, but also leads to the use of this valuated biomass, which are otherwise considered as the waste biomass, as a feed, valuated feed to produce cleaner form of hydrogen through this biological hydrogen production process. These projects were sanctioned by the Department of Biotechnology, Ministry of Science and Technology, Government of India. We gratefully acknowledge those ministries for funding, for providing us this funding support, and of course this process would not have been successful without the great contribution of the entire biofuel research team at TERI. And apart from this process, we have also explored intensively to develop the pilot scale and the large scale process for biohydrogen production by using the spent the organic discharge from, that is the sugarcane blackstrap molasses. That process we have already scaled up in 1000-liter scale. That has also a great potential for scaling up in the demonstration scale. However, this presentation highlighted mostly on the use of next generation feed for biohydrogen production, as my presentation mostly highlighted on the development of the process for the second generation hydrogen production by using the broad spectrum substrates, that is the lignocellulosic biomass, aquatic plant biomass, and the microalgae biomass. Currently, we are working intensively on development of a algal biomass-based biorefinery approach, where we are targeting to develop the processes for the biofuel and biocommodity production in an integrated manner. Thank you very much. I would be happy to take up the questions in case there is any queries. Thank you.